My name's Dr. Leon Watts. I'm a senior lecturer in computer science at the University of Bath. And this talk is to give you an idea of how computer science is conceived at the University of Bath and the kind of things that our undergraduate students encounter when they begin their studies with us. So computer science is in essence a matter of defining problems to be solved in such a way that they can be addressed with logic, intelligence, and very often invention. The combination of these three things mean that computer scientists have a key role to play in effect inventing the future, designing and inventing the future. Computer science can be thought of in many ways, but I think it's really important to differentiate the science of computer science from the engineering of bits of hardware. And to help you understand that distinction, I'd like to quote to you from a very famous computer scientist. He said, computer science is no more about computers than astronomy is about telescopes. Well, who was this man? He was a man, as it happens. His name was Edgar Dijkstra. He was a logician, a Dutch logician, and also a recipient of the Turing Prize in 1972. And Turing Prize, for those that don't know, is the computer science equivalent of a Nobel Prize. It's a highly prestigious award, the top award, actually. Now he was granted that award on the basis of seminal work he did in the design of programming languages. That's right. Programming you'll have heard of, no doubt, a matter of coding. You might have thought, well, that's the same as computer science. Really, it's using tools and knowledge that have been invented by computer scientists. So he was a person who thought about how it is you begin to design a programming language at all. He thought in particular about composition as a problem in computing based on logics. And he's famous for his work on cooperative sequential processes. That is how you, in effect, organize programs to work together. But what has that got to do with computer science? Well, or this quote, I should say. Well, astronomers, yes, they care about telescopes, but they use them for something, don't they? They're instruments that they use in order to address things that matter to them. In that case, it's what they see through the telescopes. It doesn't matter what size or shape the telescopes are, or even the nature of the information that they gather. They are in every case amplifying matters that are of concern to astronomers, and that is to do with the stars. That's what astronomers do. How does that correspond to computer science then? Well, computer scientists certainly do use computers all the time, and we do care about them just as astronomers care about telescopes. So what we're doing with those computers is we're addressing matters of fundamental computation. And that is to do with, in fact, data, representations, combinations, transformations, things that we can do. Now, I say we can do, this is not presumably, well, we can say with some confidence, it's not just a human matter. I think that's important to understand from a science point of view as well. Logics and combinations of data are everywhere in the universe. They're visible in all animal societies. Everywhere where communication happens, there's evidence that computational processes are at work. Information gets represented in lots of ways. You see here an image of the Rosetta Stone. It's not simply a matter of one-for-one correspondence of character strings, but understanding grammars, construction, and meaning as well. It's always also important for conceiving of computer science. And we can imagine that that this exists throughout our galaxy and universe, wherever there is any form of life at all. Now, we think a lot about how we can best prepare our undergraduates for life as computing professionals, whether that is to be regardless of the sector in which they might be encountering data. Now, there have been some very significant developments in the world of computing over the past few years, which have seen the maturation of a collection of technologies that are known together as artificial intelligence technologies. Artificial intelligence has a long tradition in computer science, and it is ideas associated with artificial intelligence that drew me into computing myself. Some long time ago, my first degree wasn't actually in computer science; it was in psychology. Then I was interested in thinking and how it is things psychologists call cognition, which is the combination of perception, memory, reasoning, coupled through to action. But at some point, it became clear to me that, in a way, what humans do with data and transformation is just a special case of how it is that cognition, all those things, might work together. Now, various technologies have been invented by computer scientists that address the various aspects of that idea: perception, memory, reasoning, and action, how they could be coupled together to action. But that really is what artificial intelligence is about, if you like. Now, in May 2019, government prepared a report, published a report called the AI Sector Deal, which I think is important because it shows that the maturation of those technologies, as I said already, are now gaining traction in the real world. They've been research topics for a long time in computer science, but now we're looking at things that are far more, the result of that computer science research is now bearing fruit. So to quote from the report, it says, throughout history, there have been moments when the progress of technology has taken great steps forward, leading to breakthroughs that transform how we live our lives. AI represents the latest leap, possibly the greatest leap. In the same way that Gutenberg's press ushered in a new era of growth, data-driven technologies such as AI will underpin our future prosperity. Now, that is certainly a technical matter. It's a deeply theoretical matter, but also has consequences for how we think about the utility and meaning. Remember, I used the word meaning already when talking about grammars of technologies we might invent. So to quote from Zofia Nemetis in a Guardian article in 2018, the advent of AI is about more than just technical know-how. It needs skills in judgment, decision-making, analysis, and evaluation of systems, leading to critical thinking, as well as soft skills like communication and storytelling. Because computer scientists must be able to translate the power of the tools and techniques they produce into a form that people who are facing real world problems can understand. Now, that's important because if we are to prepare our undergraduates, potentially people like you who are watching this video now, that means that our education must also encompass analysis, critical thinking, and yes, soft skills as well. Now, we're introducing some new programs as of this year, and certainly they would be programs that you would encounter if you're now thinking about going to university. That means you'll be thinking about starting in 2021 at the earliest. So that all of our programs, all of our degree programs now incorporate artificial intelligence, learning about artificial intelligence right from year one. We offer 3 programs altogether, 3 degree programs. They are the pure computer science program, computer science and artificial intelligence, computer science and mathematics. The latter of those is a joint degree delivered by ourselves and mathematical sciences. Now, what you see before you, hopefully, is a table which shows the sets of topics that will be studied by our students during years 1 and 2, which are, by and large, set curricula. Options on our degree programs are, by and large, reserved to years 3, and if you're looking at an MComp program, 4. So what does year 1 involve? It involves computer architecture, looking at computer architecture as a bridge between hardware that I've talked about. The computing has to take place somewhere. We use it to do our computation with, and the logics that we need to make sure are acting in a way that we desire through those various hardware systems. Discrete mathematics is very important to us. It is the basis of proof upon which all of our logics depend. And so our first year students encounter discrete mathematics, and they do so, or will do so from now on, in close association with relational databases, because relational databases are based on set theory, and discrete mathematics allow us to make provable connections between things that we suppose should obtain and things that in fact do. Software process, specification and testing, artificial intelligence, which I've already talked about, which covers the core set of techniques that artificial technologies now rely upon, also probability theory and ethics as it applies to the application of artificial intelligence technologies. All of our students take the AI unit, regardless of the program they're on. In other words, if it's pure CS, CS and AI, or CS and maths. They also all of our students take Principles of Programming, which is a year-long pair of modules or units, as we say at Bath University. In year 2, our students will study data structures and algorithms, a group project, which I'll say a little bit more about at the moment, and machine learning is encountered for the first time. Well, machine learning is referred to in the AI unit in year 1, but our students really get to grips with it in year 2, based on that introduction in year 1. And they also encounter 3 other areas which are very important to us at the University of Bath: computer graphics and vision, human-computer interaction, and the theoretical side of computer science. Now, this table shows each row corresponds to a unit, or in other words, a module that students will be taking. The CS and AI degree stream is column 3, reading left to right. And you'll see that, I hope you can see from this diagram, that it inherits all of the teaching from core CS in year 1. That's what it's intended to mean anyway. And everything in year 2, with the exception of human-computer interaction and comparative programming languages, where instead the CS and AI students will be taking a more advanced AI course, and also one which is specializing in the new developments in machine learning. So that's a sort of trade-off that you would make if you chose to do CS with the AI focus, is what it really means, CS and AI. Meanwhile, CS and maths students will be taking half of their teaching from the mathematics department and half from ourselves. And that means they'll be studying analysis and algebra in years 1 and 2 at degree level alongside the straight math students, exactly the same teaching those straight math students will be receiving. So that means they'll be doing that instead of computer architecture, discrete mathematics, which is mathematics of computing in effect, and software process in year 1, and instead of machine learning, computer graphics, human-computer interaction in year 2 instead. So the core units then of computer science that all of our students take are AI year 1, the introductory level, Principles of Programming, data structures and algorithms, a group project, and group project. Right. So I'm going to say a little bit about what, so give you a flavour of the kind of teaching we do. What does it mean? Because that's just topics so far. So Principles of Programming, as I said, it's year long. It's the most intensive activity all of our students undertake during year 1. And Principles of Programming involves the production of programs that are intended to be solutions to defined problems. And what that means is, part of the way we teach programming is to do problem analysis, knowing how to read programs that somebody else has produced and to produce your own, sometimes intentionally improving on a thing that you've already seen. It means getting to grips with data structures of various kinds. Lists, stacks, and queues are essential concepts in computer science, and they are implemented in a variety of programming languages. And alongside that idea, we also introduce multi-threading, which echoes back to the coordination of sequential processes that I mentioned when I was talking about EDSCADAXTRA earlier on. Our students do this by working through individual exercises supported by tutors, but also we do some pair work, it's also known as buddy programming, to try to instill the idea that programming is not a uniquely individual activity, but very often something has to be done in collaboration and cooperation with others. We have weekly programming labs. A lab means a class where tutors are present whilst our students are working on computers through programming problems, alongside 3 hours worth of lectures. So, computer architecture, I mentioned this already, is looking at what's known as abstraction layers. Abstraction is one of the key ideas in computer science. You might enjoy looking that one up, but it's essential for containing complexity as we move from one type of representation to another, whilst retaining essential aspects of it. It's omnipresent in operating systems thinking. So an operating system, something like Microsoft Windows, or Microsoft OS 10, or iOS on your Apple products, or Android on your phones. Those are all operating systems. They are commercial interpretations of layered architectures that work with abstractions to try and ensure that things stay in order when you try to get your devices to do various things. We get our students on the computer architecture unit to do individual work again, but there's a pair project work. It's a little bit different from the pair work that's done in programming, because our students engage their creative minds in the second half of semester 1 to put together some of the ideas they've been working on in the first half to come up with a creative solution to an open-ended implementation problem. And we use Arduino electronic prototyping kits to help our students understand what that means. Software process and modeling is a second semester unit in year 1, taken by CS students and CS and AI students, not by CS mathematics students. But this is different from the others in terms of the model of education and learning that we use. It's team-based learning, where we're going to assemble groups of students, around about 10 students per group, quite a sizable group, where the programming knowledge that they've gained during semester 1 is put to use in tackling a problem, a bigger open-ended problem. The reason for doing that is so that our students can start to understand how programming is done in professional contexts, in particular how the process of defining a problem for a team to solve, coming up with a requirement specification, designing code before it is in fact written, and also designing tests for code before that code is written, can be made to work effectively. We operate our teaching around what's known as an agile methods, right from the year 1 in our teaching. And they're in many ways, you can think of them as being industry standard now, best practice perhaps, although there are still many industries that are struggling to understand how agile methods can scale to enterprise level problems. That's one of the things that we think about and involve our students in thinking through in a practical way how they might do it. So software process is really engineering processes for the commercial production of software, and modeling is relating abstractions that they've encountered in operating systems, if you like, as a sort of a given and a predefined problem. For example, the OSI layered model network architecture. And to see it as something that the abstraction mechanism for handling complexity is something that applies also to coding projects that they will routinely be involved in. There are weekly group tutorials that are managed and by a team of tutors under my direction. That is, if I'm still teaching it next year. So that way we're able to work through some of the problems which are associated not only with the understanding of process and running of tests, but what it means to coordinate group work. This is very familiar to us. We've run a unit or a module around group working for a long time now. I myself have specialized in this work for 15 years, which is more longer than that now, 16 years. So we're quite well adept at helping students to overcome the inevitable challenges of expressing their ideas, listening to, appreciating the ideas of others, and scheduling their work around the many demands that are placed on them during year 1. Right, this is an example. Well, it's just because I suppose because I teach it, I can give you some concrete example of the sorts of things that our students do. This was a problem that we've used for a couple of years now, which is thinking about personal informatics management, PIM, because our students are used to doing it, or they don't realize it yet. And that is using data about themselves to keep track of some aspect of their lives that they care about and want to improve. So there was a particular group that decided it was having, the members of that group thought that motivation would be a really interesting thing to try and understand So they've organised their work around defining motivation issues and data that might relate to that. You can see that's why they called their app. They built an app called Motivate Me, and they track the process of their work using what's known as burn down charts against a sprint backlog. We're using Scrum as an instance of an agile method to assist our students in managing their work, and everything was organised around disciplined production of a specification and the active use of that specification to drive their design, implementation, and test work. So on the right-hand side of this slide, you can see what we call a test plan, which is an organised way to ensure that the things that code should be doing it is in fact doing, and if it isn't doing what it should, what exactly is it doing, so that unexpected or unwanted behaviour can be traced back through to the code that has been written related to the design and the requirements to ensure that the behaviour is brought into line with expectations. Now, the year one unit, the semester 2 unit I was just talking about, is very, very much focused on a problem that the unit leader, currently me, sets. In year 2, we move the goalposts somewhat. It's a group project again, but this time the students are asked to specify their own problem. It's a completely open-ended, student-led, student-motivated attempt to make use of all the skills and knowledge they've gained in year 1 to do something they really care about. It's a year-long project, and it allows us to help our students understand some bigger issues, professional software development and management as well. So it starts right from the beginning with a design vision that they come up with, a proposal for an idea they might work through that's subject to our feasibility judgments, right the way around to implementation and verification. And it's called an experimental systems project because it's also intended to help our students understand what it means to try testing alternatives and how important alternatives may be for pursuing an idea. It includes thinking about data collection for test, going beyond what we've done in year 1, through to the point where some entrepreneurial students might in fact be able to explore ideas for a startup company or some such thing post degree. Now, years 3 and 4 all involve optional units, and they're all based on what we're particularly good at the University of Bath, one way or another. I would like to think that any university department that you were thinking about studying in computer science, or because I know you haven't perhaps decided computer science is for you yet, it makes sense for you to think about the expertise that department has on offer and how it is incorporated into the teaching activities you would be asked to carry out. Okay. So I very briefly showed this image before without really explaining much about it. It's a representation of the areas of computer science that the UK government currently sees as being it was like a map of all the areas of that make up computer science as a whole, and also leading into the engineering sides, hardware engineering sides. The size of the bubble represents the number of research grants that are currently active in those areas. So this is really up to date. I took the image only yesterday from the Engineering and Physical Sciences Research Council website. So we can see there's optical devices, photonics, programming languages, software engineering, speech recognition, information systems, verification, all kinds of things. Some of the larger bubbles, as it turns out, are just those that we specialise in computer science here at Bath. They are visual computing, which is a combination of, well, I'll say a little bit more about them in a moment, mathematical foundations, human-computer interaction, and artificial intelligence. So what do those things mean? Mathematical foundations is how we describe theoretical computer science. It's about the logics which underpin all computing. It's it's good extra mode thinking about what computer science involves. It involves the research, invention, and verification of algorithms in various forms. Computational semantics is the study of the meaning of computer programming languages in relation to their intended operation. It has applications in the likes of cryptography and safety critical systems where you need to know the code that's written really does the job it was intended to do. Artificial intelligence, I've said a little bit about already, but it encompasses, there's two sides to artificial intelligence, really. One is understanding natural intelligence, potentially including human intelligence as well, and animal intelligence using machines as models. So if we recognize something in the world as being, it looks intelligent, it's doing a thing that's doing some kind of information collection, processing, transformation, and taking action, which well, one would, if you like, informally describe as being intelligent. And that's a candidate for investigation for computer scientists, because what we can say in looking at such a system is, what is going on? Can we describe it? And if we can describe it, how can we then make use of it in computational systems that we could create? So that's the other half of artificial intelligence, is engineering smarter machines using natural intelligence as a model. Visual computing is a combination of image generation or computer graphics and image understanding, which is computer vision. And it's a research area and leading into the teaching we do and the specialist options we offer in years 3 and 4, which all revolve around the generation of models, generation and use of models. That's data models of things by and large in the world, things that you can point a camera at and take an image of. All images are, from the computer point of view, before we apply computer science understanding, it's a big array of values, pixel values, colors, and intensity. That's all it is. There is no understanding in a camera at all. All it produces is a big table. By the application of computer science knowledge, we can do things with the values in those tables to determine whether or not there are things in them that, if you like, correspond to meaningful elements, like edges, shapes, boundaries, textures, and the like. And it has applications in the gaming industry, movies, special effects, but also in any way you want to use a camera as like a sensor in the world to do tracking and that kind of thing, tracking and control. Human-computer interaction, which is my own specialist area, well, I'm part of the efforts here at the University of Bath, you can think of it as a means of computer scientists extending the capabilities that human beings have in terms of perception, memory, reasoning, and taking action. One of the pieces of work that most inspired me was carried out by Doug Engelbart and Bill English in the late 1960s in the United States, and it was called Workstation for Augmenting the Human Intellect. That was what they called their project, but it seems to me that was a very insightful way of thinking about the potential of for computers to somehow make us more than we are. These days, that can extend to all kinds of things, including, for example, using video communication to stay in touch with those we care about when there are no other options available to us. Here are a couple of examples of final year projects. So the final year is specialist options, but it's also individual, not group anymore, but individual projects that are, I like to think of them as being an opportunity for our students to scratch an itch that they really want to scratch. In other words, to pursue a topic of interest that they care about. They really want to get to grips with something. This is an example of a project that the student decided to call Evercycle, use of VR to see whether or not people's ability to exercise could be improved. So it's that augmentation idea again. It was a human-computer interaction project. He was looking at what he called, what he and his supervisor, Dr. Christoph Luteroth, called the feed-forward effect, which is creating images in VR of a person who was exercising in the way that they wish they could. and to see that in real time through VR goggles, to sort of emulate, see whether or not the actual performance of the person could emulate that. They were doing this using exercise bicycles, and using the data from the bicycle output to drive performance in the virtual world. Another example, Holly Dent, one of my students, was very interested in running. You don't have to be fit to come to the University of Bath. The opportunities are there to get fitter if you wish. We have very good sporting facilities. It's just, I suppose, I hadn't really thought about it. It was an accident that both of these projects are fitness related. Holly was very interested in running. So I'm running in the real world augmentation of somebody's ability to get through those hard moments, and also to begin to go out for a run when maybe they're not feeling quite so good. And so she was, because I've been very interested in emotion for a long time as a research topic, how emotion makes a difference to process of reasoning, judgment and taking action, and how we might think about that as being a computer science problem, an HCI problem. How is it we could take into account people's feelings of deciding how best to assist them in taking action that they want to take? So that was an example of a final year project related to my research. We also run placement scheme at the University of Bath. It's very well known. That's another way. It's a sort of a formal way of organising monitoring and helping people to get the most out of internships with industry. Currently, about 2/3 of our students go on placement. The placement is always in the penultimate year of study. So for our bachelor students, that means between year 2 of study at university and year 3 of study, if you like. The reasons for doing a placement, some of them are self-explanatory. It's industry experience in advance. Another one is some of our students get offers of permanent employment from the placement employers they have been with for a year. And they get used to the sorts of things that people in industry really want in employees. But other things are perhaps less obvious about it. They will already be developing a professional network, which is incredibly useful in these days when careers are things that evolve and in steps that take more or less 2 to 3 years with one employer before going on to the next. But some of them also get ideas for their own final year projects, develops their own thinking about computing. In fact, they're required as part of our placement to do that, and keeping a log of the activities that they've carried out, discussing them with their line manager and mentor, if they have a mentor in the company, to think about the placement year as a career development activity. All of our placements are paid. That's something we insist upon at Computer Science. If an employer wants to make use, if you like, I don't like that phrase, but it's something that they do, make use of one of our students for a year, then they're going to need to pay for it. They don't pay us, they pay the student. They get a salary. The last time I looked at this, actually 2 years ago, salary ranges in the between 15 and 38,000 per year. Spanning a tax year, if you know about tax years, you know that makes a difference. Right. So whilst the placement, it sounds like it's a thing that you do just between your second, well, before your penultimate year of study, we prepare our students for the whole process during years 1 and 2. That includes more than assistance, really, training in how to write a CV, how to do an interview, how to approach the kinds of exercises that prospective employers often require applicants to undertake. There's a lot of assistance with that. CVs are checked, mock interviews are done, and also advice on potential companies are given. So if you think about all the things I've said so far about the relevance of our what we think about as being a relevant degree in terms of subject matter, but also the activities that our students undertake during their studies: individual work, pair work, group work, problems definition, analysis, as well as the opportunity to go on placement. Our students have very good graduate outcomes. The best way for you to it's easy to say, isn't it? Our students are really good when they graduate. They're very valuable to potential employers. look at the UK government website, discoveruni.gov.uk, where you can see statistics for any computing, any degree actually, in terms of employability. And what you'll see is for our computer science graduates, the latest survey showed that 100% were employed in managerial, professional, technical jobs within 6 months of graduation. Now, that's a slightly more refined figure than the how many have got jobs, because if you look at the percentage how many have got jobs, it undervalues those who've decided to go on to further study or do spend a year out, if you like. So the kind of job that graduates get is important. And so this is another way of saying that our students who decide they want to look for work, by and large, in recent years, all of them have managed to get a meaningful job in terms of their computer science training. Example companies, the ones you might expect, ICT companies, IBM, Microsoft, Oracle, etc. But also a lot of our students go into data intensive sectors like financial services, manufacturing. There are also there's a lot of government demand for computer literate, computer science students who are able to perform analysis, critical analysis and specification work as well. So quite a wide variety of potential jobs. There are also a number of our students who decide that they want to pursue further their interest in computer science further. And of course, because of our research specialisms and exposure to research ideas during the undergraduate studies, they're well placed to do so. Artificial intelligence, human-computer interaction, computational logic, that's theoretical computer science. Media technology, that's another way of saying visual computing. So I'd like to finish this recording by quoting from a student who's been through the program and saw one of my talks and decided that it was a thing that got him thinking. What he said was, regarding the open day, I remember the classic "not about telescopes" quote, which you've now heard, producing quite a profound clicking into place. I didn't quite appreciate how much of it is about modelling the structure of thought, illustrated by my continual amazement at how many of the fundamental concepts I learned during my degree entirely predate electronic computers. For me personally, the most surprising takeaway of the computer science degree was the philosophical side, the universal scope of the ideas learned. It makes you aware of the infinite interacting systems which make up observable reality. That was Ronan. I emailed him to say, what would he like me to say to people who are thinking about studying computer science with us? So you can see it was a few years ago now, but that's what he emailed back to me. That's just me quoting from his email. So anyway, I hope you found this talk helpful for you to think about what computer science might be as an idea, what it could be, the scope of computer science, how we approach the teaching of computer science at the University of Bath, and what we might have in particular to offer should you decide to study with us. Thank you very much.